So we're going to try one problem here that ties everything together. I'm going to give you a fresh equation, balance it by half reactions, calculate E0, calculate delta G0, and K. So we're going to do all those things, all those conversions at the end. So our reaction is IN as a solid, indium as a solid, plus Pb2 plus aqueous, making IN 3 plus aqueous, plus Pb as a solid. So first job. Balance using the half reaction method. Second job. Calculate E0 for the cell. Third job. Calculate delta G for the reaction. We've done those for other reactions already. Fourth job, the one we're adding here, calculate the K value, the equilibrium constant. And the key to that one is, remember, delta G is minus RT times the natural log of K. Again, this is at 298. K, just like we've done before. So we have everything that we need to be able to solve this problem once we look up our E0s out of our table. That stuff you'll never have to memorize. But we're going to go through and solve this. I would like you to pause the video at each stage and try and solve it ahead of me. So we're going to go through in each individual 1, 2, 3, 4. So I'm going to ask you to pause the video here in a second and balance the reaction. And then pause the video, calculate E0 for the cell. And then pause the video, calculate delta G, and so forth. I think you get the idea. So I'm going to solve the balancing of the equations using the half fraction method. So pause the video here and start it once you've got your answer. All right, so when I look at the reaction up top, I've moved it up to the top here. The thing that gets reduced is Pb2 plus. 2 plus going to 0 is reduction. 0 to 3 plus is oxidation. So our reduction half reaction is Pb2 plus aqueous plus 2 electrons, making Pb as a solid. And our oxidation process is the other participant, indium. IN as a solid, making IN 3 plus 3 electrons. So those are our half reactions. We have to balance them. We have to get the electrons to balance. That means the top one's going to be multiplied by a 3 and the bottom one by a 2. So that we have the same number of electrons produced and consumed in the two half reactions. So I'm going to rewrite the reduction, carrying the 3 through. So 3 Pb2 pluses plus 6 electrons makes 3 Pb as a solid. And our oxidation becomes 2In as a solid, making 2In 3 plus as an aqueous solution, plus 6 electrons. So we carried the 3 and the 2 through. Now we're ready to cancel our 6 electrons on both sides and balance our equation. 3 Pb2 plus 2In as a solid makes 3 Pb as a solid plus 2In 3 plus. So there's our balanced electrochemical equation. If you have trouble getting there, pause the video again and go back and work through it. Kind of see if you can see what you did wrong the first time. Next step is to calculate E0 for the cell. Again, pause the video, try to calculate E0 for the cell, and then start the video back up and we'll see if we match each other. Alright, so when I solve for E0 for the cell, I get my table out, I find the 2 electron reduction of Pb2+. And the reduction potential for Pb2+, 2 electron reduction, is minus 0.12 volts. The oxidation. The reduction potential for the oxidation part, it's a 3 electron reduction of indium that we're looking up, even though it's being oxidized, remember. So we find In3+ as our starting element. In3+ plus 3 electrons happens at minus 0.34 volts. So those are our 2 reduction potentials. We don't flip any signs. That's what they were in the table. So E0 for the cell is E0 for the cat minus E0 for the and. Remember, those are reduction potentials for the cathode reaction, reduction potentials for the anode reaction. Plug in our numbers. So cathode was minus 0.12 volts, minus 0.34 volts. So that looks like plus 0.22 volts. Yep, plus 0.22 volts. If you'd been asked, is this a spontaneous reaction or not, yes or no, you would say yes, because E0 was positive. All right, pause the video there. Calculate delta G for the reaction based on this E0. All right, so E0 is plus 0.22 volts. Delta G0 is equal to minus NF E0 for the cell. So this was we have to know how many electrons there were in the process. It's not a 2 or a 3. N in our calculation we're about to do is 6. It's 6 electrons in the balanced reaction. That's an easy mistake to make. So it's minus 6 electrons. And I think in my previous videos I've been putting 6 moles of electrons. It's really 6 electrons, so that the per mole part of our Faraday carries through. That's where I was getting my units being a little bit weird before. And so minus 6 electrons. And F was 96,500 Coulomb per mole of electrons. And our E0 is plus 0.22 volts. So we dig out our calculator. Minus 6 times 96,500 times 0.22. I get minus 127,380. Minus 127,380 joules per mole. We were asked for kilojoules per mole, so we moved the decimal point 3 places. So that's minus 127.38 kilojoules per mole. Positive delta, or positive E0 gives us a negative delta G, both spontaneous. Okay, now we're going to calculate K. And K better be a big number, larger than 1, because we're spontaneous over here, right? So spontaneous stuff makes a lot of product. Okay, so we go back to our K. Delta G0 is minus RT times the natural log of K. Now we want to know what K is. So the natural log of K is minus delta G0 over RT. We've seen that rearranged before, back in the thermo chapter. Okay? Not trying to trick anybody, but you should be comfortable with that rearrangement by now. So the natural log of K, we've got delta G0. We had these values over here. Remember, R is it. This R is the energy version in joules per mole Kelvin. So it'll be easier to plug in minus 127,380 joules per mole divided by 8.314 joules per mole Kelvin. And standard conditions, 298 K. So we plug those in. 127,380, flip the sign negative, divided by 8.314, divided by 298. I get minus 51.41. That, I did it again, didn't I? This is minus. So you get positive. Natural log of K is plus 51.4. Sorry about that. It's an easy mistake to make. I still do it, obviously. Minus delta G was negative. So we got two negatives there. They cancel out. Natural log of K is positive. So K is e to the power of 51.4. So that number on our screen, second function natural log, 2.13 times 10 to the 22, which is a very large K value. We should expect that. A good size negative delta G, a very large K value, and a positive E0. So one of the things that this points out is that it is very easy to get large spontaneous values for K and G from not a very big E0. Remember, the energies that we deal with, the voltages are from -3 to +3. So this is just kind of a mediocre E0, gave us a large negative delta G and a very large K value because of the logarithmic relationships between them. Okay?